Hello everybody, hope all of you are well, and today I will continue the chapter of chemical bonding. In chemical bonding I have already completed the discussion of valence bond theory, that is the VBT, and today I will discuss the molecular orbital theory, that is MOT. So before discussion of molecular orbital theory, you have to know why this theory is required, okay, or why this theory is introduced. So we have to know what are the limitations of valence bond theory. So valence bond theory does not able to give any suitable expression regarding the formation of coordinate bond where both the electrons are coming from the same atom. This valence bond theory cannot explain that oxygen molecule is paramagnetic, having two unpaired electrons. This valence bond theory does not consider the formation of odd electron molecules or ions like H2+. This valence bond theory also fails to explain the bonding in metals and intermetallic compounds or inner metallic compounds. Okay. So to overcome these limitations, a new theory was introduced or proposed, that is the MOT. Full form is molecular orbital theory, and this theory was proposed by Hund and Mulliken in the year 1932. Now first we will discuss the characteristics features of this molecular orbital theory. Molecular orbitals are obtained by combining the atomic orbitals of comparable energies or same energies. The number of atomic orbitals are taking part in the formation of molecular orbital is equal to the number of molecular orbital. Next, when two atomic orbitals combine, then there will be formation of two molecular orbitals of different energies. So atomic orbital will be same energies. If two atomic orbitals combine, there will be formation of two molecular orbitals, but their molecular orbitals are not of same energy. One molecular orbital will have lower energy compared to the energy of the atomic orbital, and another molecular orbital has higher energy compared to the energy of the atomic orbital, and the lower energy molecular orbital is stable, and this molecular orbital is called bonding molecular orbital. Okay, and the higher energy molecular orbital, okay, that is unstable, is called anti-bonding molecular orbital. So if we draw the diagram, then you can easily understand. So here we are showing the energy diagram. So this is the energy. So energy is increasing along this direction, okay, and stability decreases from top to bottom. Okay, this is the stability. Now if we draw the atomic orbital, suppose this one is one atomic orbital, AO means atomic orbital, another atomic orbital of same energy. When these two atomic orbital will combine, so one orbital will be formed, that is called the molecular orbital at the lower energy level, and another will be formed, the molecular orbital. So these are the molecular orbitals. Another will be at higher energy level. So here energy is low and upper energy is high. So we are getting two molecular orbitals by combining these two atomic orbitals. lower energy atomic orbital, a molecular orbital is called bonding molecular orbital. So this is called bonding MO, and this molecular orbital it is called anti-bonding molecular orbital. Okay. So here one atomic orbital is there, here one atomic orbital is there. They are of same comparable energy. So two molecular orbital will be generated, one at lower energy and another will be at the higher energy. Okay. So lower energy is called molecular orbital is called bonding molecular orbital, and higher energy and is called molecular orbital is called anti-bonding molecular orbital. Okay. Hope you can understand. Now each molecular orbital can accommodate maximum of 2 electrons with opposite spin. So if we put some electrons here, so this molecular orbital can accommodate maximum of 2 electrons and they will be of opposite spins. Okay. The shape of the molecular orbital depends upon the shape of the combining atomic orbital. Okay. Hope you can understand what I am telling. And the molecular orbitals are arranged here from this down to top, okay, from this bottom to top, okay, that is here energy is low and here energy is high, okay. So the molecular orbitals are arranged in the increasing order of their energies from bottom to top, and lower energy molecular orbital are filled up fast, okay. That is in atomic structure we have discussed above principle. So lower energy will be filled up first, then there will be higher energy. So electrons in the molecular orbital will be filled up from lower energy to gradually the higher energy level. Hope you can understand. Here also we will follow the Hund's rule. That is for the degenerate molecular orbitals, that means same energy molecular orbitals. So the electrons will be filled first unpaired, okay. Then after filling the all degenerate molecular orbitals unpaired, then we will pair the electron. Understand? So molecular orbitals are formed by linear combination of the atomic orbitals, and atomic orbitals of an atom can be expressed by the wave function psi, that is coming from that Schrödinger equation. Okay, that Schrödinger wave function equation, electron wave function is there. From there, that the wave function psi is coming. But it is not possible to obtain an exact wave function for a multi-electron and multi-nuclear system. Now let us consider the combination of two atoms A and B. Okay, so definitely if we write according to the wave function, if the atom A, its atom A and its atomic orbital, okay, and its atomic orbital, if we write in the wave function form, that is the wave function of the atomic orbital of A, if it is psi A, and the wave function, this is for the A atomic orbital. A is an atom and this is the atomic orbital wave function. Another atom we are considering, that is B atom. So in B atom it will be psi B. So this is also the B atom's atomic orbital wave function. Now there will be two cases. One will be the overlap, okay, of these two A and B, that is wave in the same phase, and another there is overlap, that is out of phase. I have already discussed that suppose this is a wave and here positive and negative signs are indicating the phase, okay, or symmetry. It is not the charge. Okay, if these two are in the same phase, when they will combine, what will happen? Definitely the resultant amplitude will increase in this way. So this is additive. Okay. So case 1, when the two waves are in phase and combine each other, okay, then the amplitude of the new wave, if we write the amplitude is psi is equal to psi A plus psi B. Okay, and another case may arise, that is when the two waves are out of phase. That means one is this one plus minus and another is this one minus plus. Then what will happen? Definitely there will be subtraction or amplitude will be decreased. Okay, so this is out of phase. So case 2, when two waves are out of phase, the two waves try to cancel out the effect of each other. Then the amplitude of the new wave, we can write that psi star, that will be psi A minus psi B. Hope you can understand. Okay. Now the addition overlap is called the bonding molecular orbital. Okay. So this one, that is psi is equal to psi A psi B. So this is nothing but the molecular orbital. The psi MO will be psi A plus psi B. This is for the bonding molecular orbital. And psi star MO, that will be for the anti-bonding molecular orbital. Okay. So hope you can understand. So this is the addition of wave and this is the subtraction of wave. So they are in phase and they are out of phase. So in this way, by wave function we can represent the MO. Okay, molecular orbital. Next we will discuss the overlap of orbitals during formation of this molecular orbital. So combination of atomic orbital. Okay, one thing you have to keep in mind when you are combining this atomic orbital, there will be two type of overlap that already we have discussed in Valence bond. Head-on overlap, that is sigma bond, and lateral overlap pi bond. Okay, but in case of molecular orbital, when we will draw this pictorial diagram, then you can understand. Suppose this one is S, so positive symmetry. Okay, this one is the positive symmetry, and another we are considering, that is the S. This one is also positive symmetry. So when these two will combine, definitely so plus and plus they will combine, and finally we will get a structure like this, plus charge. Okay, so this is what, this is sigma S molecular orbital. These are the molecular orbitals. Okay, this sigma S molecular orbital. Hope you can understand. Now if a p orbital combines with s orbital in phase, that means this one is plus and minus and another s is coming, this is also plus, then what will happen? Definitely there will be overlap. Minus plus, and that will overlap with this plus. This one is p orbital, this one is s orbital. Suppose this one is the if we consider here as p orbital, okay, and this one is the s orbital, then that will be the sigma sp. So when we will write this picture or draw the final diagram, so this plus plus, that portion will be increased plus and this portion will decrease. So this is the sp sigma. Okay, because one s orbital and another p orbital is there. So this is called sigma sp molecular orbital. Sigma sp molecular orbital. Okay. Next, there is pp overlap. Suppose if we draw the two p orbitals, pz, this one is plus minus, this one is pz, and here also these are head-on overlap, definitely plus minus, the same page. Okay, if they combine, this is also pz, then definitely there will be overlap. Plus, minus, okay. Finally, we will get like this. This one is minus, plus, and this is sigma pz orbital, molecular orbital. Okay, this sigma pz orbital. Okay, next here whatever we have drawn, okay, symmetry is same, plus is combining with plus. Next we will discuss another type of overlap. Suppose this one is s orbital and it is combining with a p orbital. Now in this case, this special type of case, that is here s is plus and p is both plus and minus symmetry is combining with plus, definitely there will be no overlap. This is called zero overlap. So it will not exist. Actually what is happening here, this plus plus overlap is cancelled by this plus minus overlap. Okay, so practically there will be no overlap. Okay, there will be formation of no bond. Hope you can understand. Now what will happen if we combine with plus and minus? Suppose two s orbital is there, one we are taking plus and minus, then definitely there will be no bonding, there will be severe repulsion. And if you draw the internuclear axis, one side this will be the plus and another side there will be the minus, and this one is called anti-bonding. This is called sigma star s anti-bonding. Okay, in the same way, if we consider the out of phase overlap of two p orbital, suppose this one is one p orbital, here it is plus minus and another p orbital is coming, this one is minus plus, so this one is pz and this one is also pz, then what will happen? Definitely there will be repulsion, there will be no formation of bond, so this will decrease. So this one is the plus minus, this one is the minus, this one is the plus. So this type of bond is called, that is the sigma star to pz. Okay, so this is called sigma star to pz. Now if there is lateral overlap in case of p orbital, this one is plus minus and another p is coming plus minus. Suppose this one is the px, this one is also px. If they will combine, what we will get? This is called pi bond. So plus plus minus minus. Finally we will get an electron cloud above the internuclear axis and one is the lower. This one is plus, another is minus. Okay, the same amount of cloud will be there, and this is called pi molecular orbital. Okay, and in this case we can write that this one is the pi to px, pi to px. But if we take the two p orbital side by side overlap, okay, but if their symmetry is different, suppose we are taking one plus minus and here is minus plus, okay, this one is px, this one is px, then what will happen? Definitely there will be strong repulsion, there will be no formation of bond. This is also anti-bonding, and this type of bond is called pi star px. We have already told you that when there is bonding, definitely it will be stable and it will remain at the lower energy level, and when there is formation of anti-bonding, it will remain at higher energy level and it will be unstable. Okay. Next we will discuss the energy level diagram for molecular orbitals. molecular orbitals energy level diagram from lithium to boron to carbon to nitrogen will be one type. Here, if we write the electronic configuration of carbon, then we will get 1s2, 2s2, 2p2. And here the energy gap between 2s and 2p, the up to nitrogen, it is very, energy gap is short. So definitely there will be sp mixing, okay, in MO diagram, and this is also called sp interaction. So here what will happen, if we draw the diagram, the sigma pz orbital, okay, so sigma pz orbital will repel with the sigma star 2s orbital. That means sigma 2pz orbital will repel with the, there will be repulsion between the these two orbitals, sigma star 2s and sigma 2pz. If we draw the diagram, then it will be clear. Okay. So this one is the energy diagram, that is up to nitrogen. Okay, after nitrogen there will be different thing. So this is the energy. Energy is continuously increasing. Okay. Now first, if we draw the diagram, then you can understand. This is for 1s, these are the atomic orbitals, and in middle there will be the molecular orbital. So this one is the 1s and this one is the 1s. So when they will combine, then one molecular orbital at the lower, another will be at the higher. So this one is called sigma 1s and this one is called sigma star 1s. Then 2s of two atomic orbital will combine. Here also one will be at lower energy, another will be at higher energy. So this one is called sigma 2s. Okay, this is the bonding molecular orbital, and this one is the anti-bonding sigma star 2s. Then 3p orbital, 3 2p orbital will come. That means 2px, 2py and 2pz. They are degenerate orbitals, okay, atomic orbitals, because their energy is same. So here also this side 3 orbital of 2px, 2py and 2pz will come. Now what will happen, that pi orbital will be at the lower, okay. So here will be the pi orbital and sigma will go above. This is the sigma 2pz. This one is the pi 2px and pi 2py. And here will be the 2 pi orbital, that is pi star 2px and pi star 2py. Hope you can understand. And sigma will go to the highest energy level, sigma star. This one will be the position of the sigma star. That is sigma star 2pz. This will be at the higher energy. So what is happening here? There is sp mixing. Okay. This type of mixing is there. And this S and P, they will be mixing. This is called sp interaction. Because of this repulsion with this sigma 2pz and sigma star 2s, so it will go at higher level above pi. Okay. So this is the energy level for the molecules like B2, C2 up to N2. But after nitrogen, this energy gap, that means between 2s and 2p, okay, atomic orbital, this increases. So there will be no sp orbital mixing or sp interaction. So we will observe the regular trend. Sigma will be more stable, that will remain at the lower energy level, and pi will be at the higher energy level. Okay, now here if we write the order of the, that means energy order, okay, the increasing energy of the MO orbitals, then what will be the order? I am showing you. So lower energy will be the sigma 1s. This is the lowest energy. Then this is the MO electronic configuration also, MO configuration. Here we have to, each orbital may contain maximum of 2 electrons, that you have to fill up. Then it will come sigma star 1s, then sigma 2s, then sigma star 2s, then pi 2px, pi 2py, then sigma 2pz will come, then pi star 2px, pi star 2py will come, then finally we will get the sigma star 2pz. So here from sigma 1s to this sigma star 2pz, energy is increasing. So energy increases. So if we want to fill up the electron, so we have to start from the lower molecular orbital to higher molecular orbital. Okay, so from here we will fill up the electrons. Another case we will discuss, that is for molecules from oxygen, fluorine, neon, this type of molecules. Okay, here a little bit of change is there in the energy diagram of MOT. This is the energy. So now we are drawing for the molecules MO diagram for oxygen, fluorine, okay, and neon also. Actually Na2 will not exist, although I am writing. When we discuss, then you can easily understand why I am writing. So first, this one is the energy is increasing. So first 1s and 1s will overlap. Definitely these are the atomic orbitals. Lower energy will be sigma 1s, higher energy will be sigma star 1s. Then 2s atomic orbital will come. They will combine, linear combination of atomic orbital will form the molecular orbitals. So it will be sigma 2s and this is sigma star 2s. Then 2p will come. Here the energy gap is very high. 2px, 2py, 2pz. They are degenerate orbitals having same energy, and 2pz. At the lower level, here there is no sp interaction, no sp mixing, so lower will be the sigma. This is called sigma 2pz orbital, and this pi will be here. Pi will be higher energy compared to this sigma 2pz. So this one is the pi 2px and pi 2py. Hope you can understand. Okay. Next, the 2 pi orbital, that pi star 2px and pi star 2pz. This one is the sigma 2pz, sigma star. Star is indicating the anti-bonding. Okay. So this is for the molecules of oxygen, fluorine, neon. Okay. So here the, if we write the MO energy, okay, that means the, if we arrange the molecular orbitals, these are the molecular orbitals according to the increasing energy, okay, then after sigma 1s, sigma star will come, then sigma 2s, then sigma star 2s, then here it will come that sigma 2pz. After sigma 2pz there will be pi 2py, pi 2px and pi to py. Then there will be pi star to ps and pi star to py. Finally, there will be sigma star to pz. So this is the energy increases. Molecular orbital energy increases from left to right. So in this way, if you fill up with electron, then you can easily understand that we will discuss in my next class how to fill up the electrons according to above principle as well as Hund's rule. Okay, so you have to practice properly to draw this type of diagram. Actually, long type of questions are not coming in exam, although they can ask to draw this type of diagram, hemodiagram. So please practice, and next day we will discuss more about this. So today up to this. Okay, thank you.